What's in a name? There are thousands of known mineral species, some with very interesting names. Here are a few examples, and trust me, they're all real. Sometimes named after the place where they were first found or after their discoverer. These examples demonstrate why names are not typically used to organise and classify minerals. The organisational structure created by James Dwight Dana is widely accepted as a classification system for minerals. This was first published in 1837, with the latest edition, the 8th, published in 1997. The Dana system is based on chemical structure. The 8 mineral groups start with the simplest minerals chemically, native elements, and end with silicates, the largest class of rock-forming minerals. Let's have a closer look at some of those classes, in particular, those that are of interest in mineral processing. If you're involved with processing base metals, then sulfide minerals are probably where the majority of your pay metal is sitting. All of these minerals contain sulfides as the major anion, and all are amenable to flotation given the right chemical conditions. If we turn our attention to the sulfide minerals that contain copper, you'll see that in addition to containing copper and sulfur, these minerals can also contain other elements, such as iron and arsenic. This may be something that you need to keep an eye on in your process. As a consequence of the different chemistries of the copper-bearing minerals, the total amount of copper in each of the minerals varies. Chalcopyrite contains about 34% copper, bornite about 63%, and chalcocite about 79%. Energite contains about 48% copper, but also contains 19% arsenic. This means that you need to know what copper minerals are in your ore so that you have a better idea of what you can expect from your process, particularly with respect to the grade of copper that is practically achievable in your concentrate. If you're working in iron ore or mineral sands, then the target minerals in your ores come from the oxide class. These minerals are not typically amenable to flotation processes. In the case of iron ores, which tend to be high grade, there are often no separation stages. Processing consists of some screening and possibly sintering to create products of the right size. Unless, of course, you're processing itabirites, which are complex iron ore deposits. These tend to have intergrowths of fine silicates. In that case, reverse flotation to remove the silicates may be part of your process. Processing of mineral sands can involve a variety of separation stages, including gravity and magnetic. Carbonate minerals tend to be acid soluble, so if the pay metal in some or all of your ore is in a carbonate mineral, then leaching may be part of your process. Carbonates are also one of the groups that contain rock-forming minerals, and depending on the type of deposit, may constitute a large component of the gangue. If you look carefully at the list of carbonate minerals, you'll see that we have 2 minerals with the same chemical formula. These are calcite and aragonite. How is that possible? They have different crystal structures. Polymorphism is the ability of a specific chemical composition to crystallise in more than one form. Here are some examples of polymorphs, and depending on their properties, it may or may not be important to know which one is present. Pyrite and marcasite have similar properties, but diamond and graphite are very different and will behave very differently during processing, and of course, they have a very different inherent value. Chemical analysis alone will not tell you what polymorphs are present. Silicates are the largest and most important class of rock-forming minerals and make up about 90% of the Earth's crust. The basic building block of the silicate group is the silica tetrahedron, and silicates are divided into subclasses according to the degree of polymerization of the silica tetrahedron. Depending on your ore type, silicates will be the predominant gangue mineral in the ore. The size reduction strategies in your process will be controlled to a large extent by the physical properties of the gangue minerals in your ore. In the case of silicates, this is largely determined by the crystal structure. Starting with the lowest degree of polymerisation, isolated tetrahedra, we have the orthosilicates. The olivine and garnet groups are part of this class. The silica tetrahedra are connected by cations, which for the olivine group are magnesium and iron. The chemical formula for the olivine group is written as shown, to indicate that either magnesium or iron, or both, are possible. And in fact, there is complete solid solution between magnesium and iron, with the end members being forsterite and fayolite. This is an example of a binary solid solution series. The garnet group has two ternary solid solution series. In the first, aluminium is in the Y site in the chemical formula, and in the second, calcium is in the X site. Minerals in the garnet group are particularly characteristic of metamorphic rocks, but are also found in some igneous types, and as detrital grains in sediments. From isolated tetrahedra to two that share oxygen, the epidote group of minerals is an example of this subclass. You can see from the formula that the chemistry of silicate minerals can be complex. Next are the ring silicates, and you can see from the mineral example here that silicates, just like carbon, can have value and may be the target of extraction in mineral processing. In the case of dioptase, the presence of this mineral may make it challenging to recover copper in your process. If your separation process happens to be flotation, then any copper that occurs in the mineral dioptase would represent non-recoverable copper. Next, we have the chain silicates. The pyroxene group is one of the most important groups of ferromagnesium silicates, or more simply, silicates that contain iron and magnesium, and occur in almost every type of igneous rock. Amphibole is a common constituent in both igneous and metamorphic rocks. It can be chemically complex and a potential source of fluorine. The basic structure of phyllosilicates is that of a composite sheet, where a layer of octahedrally coordinated cations is sandwiched between two identical layers of silica tetrahedra. The serpentine group includes the minerals shown here. These are more examples of polymorphs. In this case, it's very important to know which one is present in your ore. Chrysotile is what's known as an asbestiform mineral. You can see from the image that as a result of the crystal structure, this mineral is fibrous and represents a potential health hazard, whereas lizardite and antigerite do not. The pyrophyllite talc group have the layer structure shown. Talc can be a problematic mineral in flotation processes. Not only is it naturally hydrophobic, it's usually fine-grained and can cause the formation of very stable froths, sometimes called froth monsters, that are difficult to pump and don't break down in concentrate launders. Because talc tends to end up in the concentrate, the magnesium content of the concentrate can be high, and this can cause problems during smelting. Clay minerals tend to be present in ores that have undergone alteration. The presence of clay minerals can cause a range of problems during separation processes. This is why these minerals are sometimes called bad actors. They tend to be very fine-grained and as a result can cause significant changes in slurry viscosity, even at relatively low concentrations. This can seriously impact the efficiency of the flotation process and result in low recoveries. The last subclass of the silicates are the framework silicates. The quartz and feldspar family are in this class and are the dominant gangue mineral in many ores. A rose by any other name, or in this case, a mineral by any other name. As we've seen, names don't really tell us what matters about minerals and how they might behave during processing. Systems for classifying minerals, such as the Dana system, are a useful way of organising the more than 4,900 mineral species that have been identified. Do you know what minerals are present in your ore?